look at it as like
Okay.
yeah, so they really do talk as if they're related.
Why isn't there an infinite dimensional determinant?
Yeah.
Okay, today we have Vaughn who's going to tell us about why there's an infinite dimensional version of the determinant.
Yeah, why there isn't.
Why there is not.
Where there might be.
Where there might be.
Yeah, okay. I guess the first half of the talk I wrote just as a construction of the determinant. Has anyone seen that before, or how many people have seen that before? Okay, I'll do it. Nice. Okay, so I guess when I'm constructing it, I'm going to try and avoid. Well, okay. What do we want? What do we want? We want a map in the finite dimensional case. We want a map going from linear operators on V into, I'll start with R, and then I'll switch to C later. So what do we want geometrically? We might want some, I guess, let me start with a few properties. I'm just going to write them down and then I'll explain why I think they're good. So we want to we want a number that represents the area scaling, right? I'll call it volume scaling. Induced by some linear map T, right? We also want something that can keep track of whether or not something's a reflection. So what do I mean by reflection will become more clear later. So I'll just say keeps track of reflections. So so this is one set of properties that, if you interpret it in the right way, will give you a well-defined determinant. And by well-defined, I mean that it's defined and that it's unique. So there's not multiple choices that would satisfy these types of things. I'll give a set of algebraic conditions, and let me write them down first. So we might want, let me number these actually. And this one will be 1. So this is probably the most important property for the determinant.
Sorry, you wrote B twice.
Oh yeah, you're right. Yeah, so we want multiplicativity, and we want, and I'm going to write this. I'm going to write det. So I guess this is kind of motivated by the previous, what I was saying up here. So if it scales volume, if we have a lambda here, then we want, as we pull the lambda out, it should go up with the dimension of the space. And okay, I guess this is a good time to mention, I think for those of you who already know what I'm going to be doing, try and think about how it might generalize to infinite dimensions as I'm doing it. Maybe that'll make it more interesting. Okay, so yeah, we want these properties, and then you also have to put in one more. So continuity. So I haven't put any topologies on V. So we're going to do this one first. And this is what we use to show the existence, I guess. Okay, I said I was going to explain why I wanted this property. So why do we want this? Well, okay, let me explain what these correspond to. So say we have some epsilon going from B to C, going from B to C. So this is some function that will take in 3, in like the n is equal to 3 case. I'll draw a picture. What it does is it takes in 3 vectors. Which specify like a volume. And then obviously the picture generalizes. So what we want it to do is give us whatever this volume is, right? But how do we find that without any structure on V is not obvious immediately. So we can start by just asking, well, what properties would we want it to have? So if I swap E1 and E2, for example, let me draw like a different color. So this is something like a reflection through here. It's kind of a bad angle. Let me go like. Right, and so what I'm doing is if I swap E1 and E2, I'm reflecting the I'm reflecting the volume along that green surface. So that's one way we can reflect. And so what do we want if we do this? I want epsilon of E1, E2, E3 to be minus epsilon of E2, E1, E3. And another way you can reflect this cube, I guess, is by picking one of these vectors and I'll get a different color again, and scaling it. So say I move E1 down to minus E1, and now I have a new volume. Right? And this should, oh yeah, what
the green one should be like E1, E3 that you're reflecting. So E1 and E2. It doesn't matter.
Oh, yeah, sure. I'll just relabel these instead. But yeah. I'm swapping these two.
So, like, I understand from a multilinear algebra point of view why swapping them gives up a minus sign, but I don't understand from your picture why does reflecting across that thing give me a minus sign? And why should the volume pick up a minus sign when I reflect it? Like, purely geometrically. Like, I understand, obviously,
Sure.
the answer, but...
Yeah. Okay, I guess there's another way of thinking about it. So if you want to think about the sign, or I guess whether or not the cube has been reflected as like an orientation.
Okay, yeah.
What you can do is the numbering of these three, for example, in 3 dimensions. What I could do is draw like a loop going in the direction of the indices.
Mm-hmm.
So okay, I relabeled these and both of them are 2 now. This one should be 3, I think. So let's say I'll draw another vector, make it thick so that I can differentiate it. So if I draw like a loop around here, this is going from E1 to E2 to E3, sort of. If I reflect it, so now I have E1, E2, E3. That's orange. That's like that's going to be going this way, right? And so now if I take these two and like try and put them in line without intuitively changing their orientation, right? Without mirroring either of these two arrows or these two loops, then they'll end up being like facing the opposite direction. Yeah, that's right. So one of them will be facing one way and one of them is the other way.
Okay.
Okay. So, but that is to say that we want multilinearity and this anti-symmetry property. Yeah. So I'll call this. I'll say denote by alt sub k of v. These, I guess, I'm just saying these maps, right? So these are the maps that I can swap any of these two entries at the cost of a minus sign, and I can, and they're multilinear. Okay, but there's actually, generally, if you go to n dimensions, it's not, to me at least, immediately obvious that this isn't empty. So how do I know that I can't swap enough of these? You know, imagine I could mirror a cube enough times in a high enough dimension that I get back to what I originally had, and say I mirror it an odd number of times, then that would be saying that the volume of that initial cube was 0, right? Because if the volume is equal to negative of its own volume, then it's 0. And so we want to make sure that this space isn't trivial. So okay, and the answer is no. Otherwise, it would be very interesting.
By trivial, you just mean empty?
Yeah. Well, what would be the other option?
Like if it's a vector space, it might be 0.
Oh, so that is what I mean by trivial, yes. So obviously 0 satisfies all of these.
Yeah, okay.
Yeah. No, you're right. Okay, so I'll talk about the wedge product for a second. And I'm just going to define it. So if I have k copies of v, I can define this space wedge. Oops, what's the name? I can define wedge to the k of v, or you can call it v wedge to the k. I think I'll tend to use this more. So basically, this is like the algebra of vectors that satisfy this kind of property, where v1 wedge v2 is equal to minus v2 wedge v1. The way that you would define it formally, which I'm going to talk about now, I don't think it's very interesting, but I think it's nice to know how it works, and then I think we'll be using the formal definition more when we go to infinite dimensions. So how do we define this? You basically, I'm just going to take 2 seconds. You start with this free vector space of V. Does everyone know what that is, or should I define it? Okay, I'll define it. So f of V is f of any set. I'll call it. I should call it f. What am I using? I'm using R. R of any set V, I guess, is basically you just take all the elements in V and you define each one to be formally like a basis element. So imagine like if I had R of 1 minus 1, then you can think of this as like this space which is spanned by elements like C1, 1, plus C2, minus 1, this type of thing, right? So I just start with some elements of a set and just turn it into to a vector space. So this is a really huge vector space. It's a vector space of elements in a vector space. What's up?
I don't know if like, is the word turning it into a basis like correct? Because I'm imagining now what if you have like a set with like all the same element.
All the same element, what do you
Yeah,
mean?
it says 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, repeated over and over.
Well, I don't think you can have, oh, I guess, so if you had,
Like, do you
well, I guess I
find
don't know
out
what you
to
mean.
make the book
Sorry?
class or whatever?
You need a linear independence.
Yeah,
Well, that's what I'm asking, if the word basis.
That's what-
is-
that's what I mean by
Sets don't
basis.
count for- right?
yeah, you can't have an actual repeated element. You could have like 0, mark it with something, but.
Okay, okay.
Okay, yeah, so basically what we're going to do is start with this, and then without talking too much about it, you just quotient out by the properties that you want. I guess I'll start with just quotienting out by the tensor product relations. So I'll just write it like this. So if I quotient out by these tensor product relations, then you end up with this space, and this should be, I made a mistake here, this should be v to the k. Yeah, so this is k tuples of elements. So you can think of it like so the elements in this in the tensor product now are equivalence classes under whatever relations we want, which are going to be essentially just multilinearity in all the v's. Yeah, these are the elements of this space, and you would write this like this: v1 tensor up to vk. And just to be explicit, I'll write it over here. The relationship is a v1 tensor v2 is a b v1 tensor v2. Okay, so now we have the tensor product. So if I want to get the wedge product, I can start from here. I can do it straight from here, or I can start from here and mod out by, since these are all the same vector space, I can mod out by swaps in the, yeah, what's up?
The tensor product, I think you still need the relation of like v1, v2 plus v1, v2 prime is v1, v2 plus v2 prime.
Yeah, okay, you're right. I need something like this. Is this what you're saying? V plus W tensor Z, whatever it is, right?
Yeah.
That's what you're saying?
Yeah. I don't think that's a good thing.
No, it's not. So you need these two things. Okay. Okay. So then what we would do is, so now this is the kth tensor of this space. So now we want to define the wedge by this space that we had, tensor k times, quotient out by these relations, I guess. And now instead of writing this as v1 tensored up to vk, I'll write it as v1 with these wedges in between. Okay, so essentially, the question that we want to ask is, so I guess I didn't finish talking about this. So this elements of this form, we're going to do the same thing where we quotient, and the relationship between the vectors is v1 wedge v and w. V wedge w is always negative of the swap, right? And so this is exactly the property that we want in the arguments here. And so what we're going to find is that these types of maps are in correspondence with maps going from essentially maps that live in the dual space of this space. So V wedge K dual. And they're very similar. And so if we want to find if any of these exist, we can just find what's the dimension of this space. And so if we can find the dimension of this, yeah, then we're good. So what's up?
Do you mind just writing that W a little more clearly?
Sure. So, okay, so what do we want? We want to find the dimension. Okay. I'm certain all of you already know the answer to this, but let's talk about it. So, again, we want to show that it's not empty, right? I could just take something from it and not think about the dimension, but we want to know, we want to show that it's not empty. And the way that you do that is by talking about permutation groups. I'm just going to assume everyone knows what that is. I guess sign of a permutation. Okay, so how do you know the sign of a permutation is well defined? These are maps going from 1 up to n, back to 1 up to n. There's a really fun way of proving this, I think. So I guess I'll say lemma. So the map by delta of any permutation is, which is defined by the sign. So this is the sign of the real number that I'm about to write down. So 1 less than or equal to I, less than j, less than or equal to up to, we'll make it k, because that's what we have right now. So, and this is, in the brackets, I'm going to put sigma of j minus sigma of I. So this whole thing, is multiplicative. And the sign of s is equal to -1 when s is a swap. Right. So by swap, I mean any two cycles. So anything that takes two elements and swaps them is the most. It's the most simple permutation that's not changing anything. Okay, so how do we know? How do we know this is true? I think I'm mostly going to say it because it's kind of annoying to write down. But so say I have two elements from 1 up to n. I'll say a to b, a, b, a less than b, and 1 up to n. So if I look at the I and j's, right, which are sort of on the left or on the right of this product, meaning, I guess meaning in one case, so we have b is the largest one. So if b is less than I, right, then really what we have is a less than, I guess, like this. B less than I gives us, in general, a less than b, less than I, less than j in our sum, right, or in our product. So basically the point is, oh my god, I haven't written down what I'm saying. So I'm saying s of a is equal to b, and s of b is equal to a. So it swaps a, b. So s is equal to a, b.
And fixes everything else.
And everything else is fixed, yeah. It's a swap, so. Yeah, so I'm going to calculate delta of s. I'm going to calculate delta of s. Okay, so let me explain what I just said, because I didn't explain what I was doing before I did it. So, yeah, so if I start with the elements on the left here, on the left of the I, nothing is going to change, essentially, right? So I'm, okay. This is actually what I'm calculating. Delta of s sigma. So nothing is going to change from this sigma when I swap one of these two i's in this argument here, right? What you need to do is go somewhere in between the I and j in order to find anything interesting happening. Does that make any sense, or did I just stumble over my words and not explain that very well?
I'm
having a hard time grasping it. So, maybe, okay, so the function you're defining is delta? Is that your symbol
Yeah, that's a
there?
delta sign.
And then you say, but under that you're saying that the sign of s is -1. Do you mean to say that delta of s is -1?
Yeah, but delta is the sign.
Delta is, okay, so this is what we're, okay. But then the sign that's beside the product, that just means
Yeah.
like how many negative, if it's -1 or not?
It means if it's negative or positive. This sign, you mean? This sign? Yeah,
That
so
one, yeah.
that was a different sign than this. Yeah, no,
Okay.
yeah, I'm trying to define the sign of a permutation. I'm just showing that it's non-zero. Or showing that that it's well defined, yes. Okay, so, yeah, so, yeah, I'll just go through some examples. So, yeah, I'll just go through some examples. That's what I really want.
Examination.
Exactly. By example. So if I go to the left, go to the left of the product. So I'm saying b less than I in this case. Then I want to look at the factor that has some I and j, right, which are greater than both a and b. Well, they're both greater, right? We're looking at a swap. If it's swapping the arguments, right? If S is swapping these I's and J's, okay, but it's only swapping A and B. But so if we're before I, none of them get swapped, so no change.
I think I see what you're saying. So like if you have your fixed A and B,
Yeah.
and you're looking at all the possible ij's in this product.
Yeah.
When I is bigger than B, you're just getting ones. And when j is less than A, you're just getting ones. So
Yeah.
you're
By
only-
one you mean it's not changing anything.
Yeah, the difference between them is positive.
Yes. Yeah. The difference is positive. Yeah.
Okay. And so the only interesting thing happens when like one of A or B is between.
Exactly. Yeah. Yeah. So the reason that I wrote it like this is because this keeps track of whether or not I's been swapped with J. Or not swapped with J, but whether or not I and J are out of order.
Yeah.
Right? So we're counting the number of elements that are out of order, and then giving that a sign. Okay. Yeah. Okay. So next we can go look in the case. You know, let me just get my notes here so I can look at how I wrote this down. I'm not explaining this very well. So. Let me actually write this down so it's clear what I'm saying. So in this case, in this case there's no change. Also, in the case where this A and B are both to the right of I and J, so for the case J less than A, right? So both of these cases are finished. Okay, so let's think about the case where in the product, only one of these two things is either an A or a B, right? So if neither of them are an A or a B, nothing gets swapped. It's just one. There's no sign change. What if one of this I or J does get swapped, right? Then what happens, right? How does the sign of this change? Yeah. So. Essentially, we don't know how the sign of it changes, but we do know that if I'll say if one of I, J is a B in the product, right? Then we're gonna have sigma of J minus sigma of say A. I'll just put it there. This is equal to, well, let me just write over this. So I have this one, and on the other hand, I have, how do I write this out? Sigma of J minus sigma of B, right? So both of these terms live in the product. And there's, as long as I only have one of these two things equal, both of these will exist somewhere within the product. This sign is always, I guess this is always positive.
Because it's like if A swaps spots with J, then so does B.
Exactly,
Because
yeah.
B is where A used to be.
Exactly, yeah. So if this goes from being less than j to being greater than j, then this has to go from being greater than, I guess, sigma of j to being less than. So if one of them swaps, they both swap, and it's positive. If neither of them swaps, nothing swaps. Okay, so what about, there's one last case that we haven't covered. The case where A is equal to I, and B is equal to j. Well, in this case, they get swapped, and you pick up a minus sign. And that's it, right? So delta of what I've just painfully explained, maybe not very well, is that delta of sigma is minus delta of sigma times s. Okay. So, and as an easy corollary, you get delta of s is equal to delta of 1 times s is minus delta of s. Okay, hopefully that wasn't too. Okay, so
It's minus 1, right?
is that what I what I wrote? No, it's minus yeah, minus 1. Yeah, that's right. Yeah, minus 1.
You gotta be panicking there. What the heck does that mean?
Okay, yeah, this makes more sense. Okay, fine. Okay, so that essentially works to show that the sign is well defined. Is that obvious, or should I explain that? I don't know why I'm asking. I'll do it. This is where I'm at. Okay, so now, I guess as another lemma, I'll say, so the permutation group of K is always generated by, I'll say, the swaps of swap of K, meaning the swaps that live in sim, right? The swaps that live in the permutation group. And I'll just say, it's obvious. Okay, I think that's, I'm not going to talk about that. I think it's mostly intuitive. So if I want to shuffle a deck of cards, I can do it by changing one at a time. That's what I'm saying. Okay, and so together, these two give us a well-defined sign. So why is that? So any sigma in sim, okay, we can write sigma as S1 up to SL, right? And so if we know delta of sigma is defined, right? And so this has to be, -1 to the L essentially, right? Because we've shown that it's a homomorphism. Okay, and that's all you need actually.
I think, yeah, you also need that, like,
What's up?
if you can decompose sigma into swaps, then if you have a different decomposition, it only goes up by 2 or goes down by 2.
Right, but that's exactly what this proves.
Oh, is that okay?
So if it were to go up by 1, then I would have shown that -1 is equal to 1.
Oh, I see. Okay. Oh, because you add an S.
Just the research.
Okay.
Oh, there it is. Yeah, exactly. Okay. Okay, let me remember where I'm going here. So I'm just gonna do this now. So the dimension of this wedge to the k is equal to n choose k, where the dimension of v is n. Okay, so the proof is basically we start with right. Remember when we were constructing this right over here? Start with the basis that we have for v tensor to the k. So yeah, let me just write this v1 tensor up to vk. Put them as v's. So if this is a basis, this is always a basis whenever ei, I from 1 to k, basis for v, and that's, I'll just say that's obvious from the way we constructed it. Okay, so how many of these elements, when I do the second quotient, how many of these elements stay linearly independent, right? We know that in our quotient, this set is going to end up spanning, right? Because it started as a basis for the original space. When I do the quotient, how many of them can I throw away is what I'm asking, and then we'll have found the dimension. So I should have written e one up to en, no, I shouldn't have. What am I doing?
You can do like E1, I.
Yeah, you're right. Yeah, ei.
Yeah.
Okay. Is a basis for that. Yeah. And this should be an F. I got all my letters mixed up. Okay. That's right? I think. Okay, so now let's quotient this. So ei1. I'll just go on a case-by-case basis. So if any of the two elements, I'm sure everyone already knows this, if any of the two elements are equal, right? So any of these basis elements where I have a repeated index, they're all 0. And so they're not even like spanned by the other ones. It's just 0. So I'm just going to throw them out automatically. So we're going to start by, we know that our basis is at most going to contain, how do I explain this? So actually, I'll do it like this. So if I have an ei1 wedge I k, let's suppose I were to write it in a different order, right? That would correspond to picking some sigma from sim of k, and asking, I guess, write it in a different order and ask what are they? This would be sigma I1 wedged sigma I k. Okay, but if I perform, L many swaps to generate sigma, as I did over there, then I'll pick up a minus sign, which we showed is going to be either a minus or a plus. It can't be both. And so essentially what I'm saying is one of these is linearly independent or linearly dependent on the other. So this is going to be either plus or minus that one. So we can always throw them out as long as I've picked a different order, right? So in other words, we can reduce this to just picking. We can reduce the cardinality of the basis to. We only have the elements which. Okay, how do I?
Yeah. So like you're only throwing away those basis elements where there are repetitions. You're keeping the ones where they're all distinct.
So yeah, you're right. I threw out all of the basis elements where there's a repetition, but I also want to throw out.
You can like ignore the ones that are out of order.
Ignore all the ones that are out of order. So I don't really care which one you want to keep. because they're all linearly dependent on each other, like pairwise, so very strongly linearly dependent on each other. But essentially every choice of a subset of K is what I'm trying to say. Every choice of a subset of this set for size K will give us one basis vector. Okay, so how many of those are there? E wedge to the K is n choose K, right? Because the number of subsets of a size n set, which are size K, is n choose K. Okay, cool. So a lot of work for something you already knew, but hopefully it was fun seeing the proof. Okay. So now we've finally proven that the space that contains our volume forms is non-trivial. It's not zero or empty. So as an easy corollary, the dimension of v wedge to the n is 1. So this is actually really important. So the fact that it's one-dimensional. So not only is it non-trivial, but there's really only one linearly independent vector in the space. So what I've shown essentially is now when I pick an epsilon in this space, alt of v wedge n, right, which remember is isomorphic to v wedge n star. The dimension of v wedge n star is just the dimension of v wedge n. In other words, if I specify epsilon on just one set of vectors, it locks it in. So this is I think this is really nice. So if you yeah, I'll do this part right now. So if I okay, so now you're going to find out why I was using epsilon. If I take, so everyone knows what the this epsilon sub I1 up to I k or IN is just the sign of this permutation that sends 1 up to n to I1 up to IN, right? Sign of this permutation. So here's what I want to do is let's set a basis. E1 up to En. I'll just say E1 up to En. As a basis for V. So what I want to do is pick epsilon of E1 up to En is 1. Does anyone know why? Why would I pick that, like, philosophically?
It's kind of like the identity permutation.
Sure. Yeah. Okay. Yeah. So if I start with a basis and don't do anything to it, I'm just saying that the volume defined by this n set of vectors is 1. So whatever parallelogram I'm starting with here, or parallelepiped, defined by these n vectors, I assign it volume 1. Okay. And that defines the whole thing, right? Because I took epsilon to be in alt. Epsilon is in alt of v wedge n. So I'm just going to write down a map also epsilon of, okay, like this, in of v1 up to vn. So using the like Einstein notation, this should be I1 of time, right? So this is using the Einstein notation. Just sum over these. This is antisymmetric and multilinear. So this, I'll say, the thing that maps VI1, VIN to this is in alt sub n of v. Why is that? Is that obvious? So if I swap two of these vectors, you can write this. Wait, what have I done here? I did something. It should be this, right? So we have these vectors v1 up to vn. Sorry. Map v1 up to vn to v1 as a vector. This is the vector v1. Now take its I1th component. That's what it should be. Okay, and now we can multiply them because they're numbers. Vn and take the inth component. So why is this antisymmetric? If I swap any two of these, right? Take care, Tom. It's equivalent to swapping one of these in the subscript of the epsilon, right? Because say I swap two elements, well, it's commutative, so I can just reorder it to how it was originally, and apply a sigma in each of these, and I'll get the original permutation back. So this is in alt sub n of v. And so as I guess I'll say and epsilon I1 up to In of E1 I1, right? Oh god, this is E1 I1. This is the I1th component of the first basis vector multiplied by the En In. So this is just, one of these things is just going to be a delta, like the first one is delta 1 I1, right? That's the, whatever the I1 component, or, in general, take something like IK or whatever. This is just 1, right? Because the only one that isn't going to be 0, the only one that doesn't have one of these things being 0 is the entry epsilon 1 up to n of just that, right? And then you're going to get a bunch of 1s in order from these deltas. And this is just 1, because this is the identity permutation. So this gives us a nice formula. So basically what I'm saying is this is the determinant, right? If you have a matrix with these columns, you can compute it like this. And it's kind of nice that you can arrive here without appealing to any structure on V other than picking this basis. And in fact, it's going to turn out you don't even have to pick the basis in order to get the formula. So if I want to turn this volume form, I guess, into a determinant, what do? You say, I want to map from ln of v, right? This is what we want to do originally. We want to map from ln of v into into R, such that which is given by. Let me look at this diagram. I guess this is what the determinant really is. We have this natural map, len of v into len wedge v wedge to the n, right? So what is this given by? It's given by the only thing it could be, which is phi of a applied to one of these big wedges, v1 wedge up to vn, is just going to be apply the a to each entry, right? So this is what would give us our matrix columns in the formula over there. Yeah, so, and why is this basis independent? Well, there is this kind of universal property, I guess. So for any map from len v into, I'll say any map epsilon from len v into, well, in fact, I'll just call it determinant. Yeah, any map, which we'll call a determinant, from len v into R. There's this unique map, which call it by determinant tilde, such that the diagram commutes. And so what do I want here? What property do I want out of the determinant? It's exactly the properties that we outlined before. It's just that wait, so I guess previous page. So I think you can lift this from this like other. I guess this is the real universal property. This isn't so much a universal property. This is like this wedge map to v wedge to the k. We have the existence of a map going this way, so long as we have a map going this way, given by epsilon. This is the map that we had earlier. So if this goes into R, right, then, and epsilon is like in alt, alt sub k or whatever, right? I'll call it n because we're going to R here. Alt sub n v. So for some epsilon here, for some epsilon in here, there's a unique epsilon tilde, which makes the diagram commute, and that's exactly what I want to use here. And why is that again? So,
Well, is it just from the tensor product? If you have like a multilinear map coming out of v to the n, then you get a linear map coming out of the tensor product. And you just have to make sure it factors through the wedge product.
yeah. Yeah, this is just some linear map, I guess. What do we want to call this det? Let's call this like f. It's a linear map, or yeah, sure, f is a linear map. So this is something which picks basically a number. F is just a number, right? It's taking something from this one-dimensional space, mapping it to this one-dimensional space. Yeah. So v wedge to the n is one-dimensional. Len v wedge to the n is one-dimensional. Map to R. So we're essentially picking a number, what I'm saying is, basically, I'm trying to say that if I specify det of any matrix, that'll give me a uniquely defined determinant. And the only one that could possibly satisfy what we want is det of 1 is 1. Yeah. I don't know if that makes any sense.
To me, the way I see it is that, like,
Yeah.
if you have like phi a, like that formula you have up top, it has to be a scalar multiple of v1 wedge up to vn, and then that just is the determinant.
Exactly. Yeah. Yeah. This map phi is the determinant, is what you're saying.
Yeah, and it's like it's a unique like
Mhm.
scalar,
Yeah.
and then you just have to fix one value for v1 wedge up to vn for some of those.
That's exactly right. Yeah, and that's what f does. F is fixing some value on some operator, right? That lives in here. And so for each these f's and determinants are in correspondence for each value in here that I fix. It'll give me an f, and that'll also give me, just by composition, this map here, and same thing the other way, right? Okay. Okay, and let's move on to the speed here. I probably have to speed up, right? How much time do I have left?
Less than an hour.
Okay, we'll go fast. Okay, so as a corollary, we're going to get det of AB is equal to det of A, det of B. Okay, so I'm just going to pick some epsilon to do this. So we know that let's say the map omega, which takes v1 up to vn and maps into maps to epsilon a applied to v1 up to a applied to vn. Is this the right map? Yeah. Actually, let me rewrite this. I'll just say the map epsilon. Yeah, that was the right one. Sorry. Yeah. Maps to epsilon of a v1 to a vn. I'll just call this epsilon sub a, right? So it takes what we already had in our epsilon and just pop an a on the left in each entry there, basically. Okay, well, guess what? Epsilon a and epsilon are both elements of alt sub n of k, or alt sub n of v. Right? So what am I going to use now? It's one-dimensional, and so we know epsilon sub a is necessarily equal to, I'll just call this lambda a, which is some scalar of epsilon, or times epsilon, right? And that gives us epsilon a of epsilon of ab e1 times ab e up to en, right? This is, I'm going to pull the a out, ea, b, e1 up to b, en. I get to pull the lambda out, lambda a of epsilon of the same thing. Yeah, and then how do I finish this off?
I have a question that I was going to ask before, but now with this corollary, I'm even more curious.
Okay.
The commutative diagram for the universal properties in what category? Because if it's, I thought it was in the category of algebra, so this would be obvious just because.
Yeah, I don't know, to be honest. So, I don't know.
Okay.
It's just vector space.
Yeah, I'm not using any structure other than.
Like it cannot be the category, like the one above cannot be, because like determinant is not linear with respect to vector spaces. So that's why I was.
Yeah. So yeah, this isn't. I don't know. It's not. I don't think it's. I think it's not really a universal property. I don't think it's just like. I'm just saying that if you pick an f, it forces you to pick this determinant, and if you pick the determinant, it forces you to pick an f. So I don't know. I don't know if anyone has a better answer to that question, but yeah. Okay, so okay, and this is epsilon of b. This is just det of b, right? And this is det of ab. Okay. I'm not following what you're saying. All right. Okay. So what? Yeah. Okay. And also lambda a is equal to lambda a times epsilon of e1 up to en, right? Which is equal to epsilon of a e1 up to en, aen, which is det of a. Right? So the lambda a really is det of a, and when I pull it out here, I'm saying this is det of a times det of b. Okay, now I'll give, do I have time to do this? I might skip this part. Okay. I'll go really quick through and then I'll go to the infinite dimension case. All these are in here. Oh God.
It could be just groups, right?
Yeah. Wait, I think it's after that.
Oh, yeah.
Not every linear transformation is vertical, so it's not just going to be groups.
They're like nice enough with respect to products, not every. I think.
Monoids.
Okay, so I'm gonna take C to be a vector space. Everything we just did, I picked R. I don't know if it didn't really matter. You could pick C as well. I just picked R because when I was drawing that picture at the beginning, I feel like it makes more sense what I was really, like why would you want these properties, I guess, not instead of just pulling them from thin air. But yeah, you can easily just pop a C in there and it changes nothing. And C is algebraically closed. So we're going to use C. So what were the properties I wanted? So okay, I wrote these down, so I'll talk about it as quick as I can. So we built a determinant from this, and actually, did I finish? So actually, I showed that they were that det of a is multiplicative. It's also really obvious from our construction that det of lambda a is equal to lambda n det of a, and that it's continuous. So this is true, and det is continuous. Cool. Okay, so delta, suppose delta satisfies, I'll just call these properties.
It's continuous because it's a polynomial expression in the coordinates.
Sure, yeah, that's, yeah, exactly. So, and delta satisfies and I'll call it heart. There we go. So meaning these three properties. So I want to show that when I pick this delta to satisfy these, I'm going to get the same determinant that I got before. I picked this one. You can think of this sort of equivalently. It'll be obvious that it's equivalent in a second as this. So if I have the direct sum of these two operators, this is going to be determinant of A times determinant of B. Right? This is just saying if I have a block diagonal matrix, I can take the determinants of the block diagonal entries. Okay, so if I take delta to satisfy these properties, well, right away from the multiplicativity, I don't. I can define it up to similarity, right? So as long as I have it on one operator, it's defined in the whole conjugacy class of operators. Also, I'll say, okay, without proving it, I'll say the space of diagonalizable operators in Mn of C is dense in Mn of C. I guess I can just call this diag sub n of C. Let's do that. And so why is this true? You can get here from a few different ways. One way of looking at it is so if I have an operator A, say an arbitrary operator in Mn of C, well, A has a Jordan form, so A is equal to, say, S times this Jordan matrix, like lambda 1 up to lambda k1 or whatever with these ones, right? Lambda k2 with the ones, etc. On and on up to lambda kl, right? So we have this matrix with all these Jordan blocks. I should put an S inverse here. So all I want to convince you of, it doesn't really matter what's in the top diagonals, right? There's some stuff going on in the upper diagonal, but the diagonal entries here are the eigenvalues, what you consider the generalized eigenvalues. So if I perturb these eigenvalues by a teeny bit, each one, I can remain as close as I want to A, right? And after perturbing them so that they're all distinct, because of the way that this is written out, you can see that it's going to be continuous in the changing of the eigenvalues, so I can remain close to A. And the second they're distinct, I know I can diagonalize it. So that's basically the whole argument. Yeah, I guess I don't have time to get into it further than that, but
Like, is this where the continuity actually shows up? Because we didn't mean anything about continuity.
yeah. So I tried really hard to get these two properties to work, or like, I tried hard to get them to work without the continuity, but I couldn't get it to work. And it's going to turn out like when you're in infinite dimensions, I think you want continuity anyways. But yeah, I don't know. I think there's probably some way of doing it without this.
I think so, yeah. When I took like math 245, I don't think we used continuity anywhere, but we still did this whole thing.
Yeah, I don't think you need it. But I think if you get rid of it, it's harder maybe to use this property.
Maybe.
I think you need to strengthen it to this.
Yeah, I don't remember.
Fair enough. Okay, yeah. Okay, so this is where I'm going to use the continuity. I'll say here's a fun argument. And I've got this like lambda to the n property just because I think it's makes it really obvious that this is really the only thing that could possibly like give us a volume, right? Like if I resize it, it must resize it by the size of lambda to the n. Okay, so if I have basically I want to say what's the delta of a diagonal matrix, right? So I've shown the diagonalizable matrix are dense. I've shown that they're only defined up to being similar to other matrices. So if I can find that delta is defined on diagonalizable matrices based on just these properties, so it's determined, I guess, on diagonal matrices just by these properties, then it'll be determined everywhere. So delta of lambda 1 up to lambda n. I guess I'll say
you have the determinant for the Jordan, but it's not so obvious. Yeah, okay, sorry. I thought you could just do it for the Jordan form, but that's because I already know the formula. You're just going to take
Yeah,
the
yeah,
product,
yeah.
so yeah.
It's it. No, I was thinking about this and the same time this took a while. Okay, so all I'm going to do is take the nth power of this. I want you to notice that I'm allowed to, for any diagonal matrix, you're allowed to reorder the diagonal entries without changing the output of delta, right? So, and that's because reordering to diagonal entries is the same thing as applying a similarity given by a permutation. So a swap like this and then a swap like this will swap two of the diagonal entries, right? So you can find that from this property. You're allowed to reorder diagonal entries. So when I apply this delta, what I can do is pull it apart, pull the product apart, and say, okay, look at the first one. Let's leave it as is. Next one, take all the lambdas and cycle it over. So it's going to be something like delta lambda 1 up to lambda n times delta of lambda 2 up to lambda n lambda 1, right? And then on until I get delta of lambda n lambda 1 up to lambda n minus 1. Does that make sense? These two things are equal. Right? And so all I'm doing is I pulled the product apart into a bunch of these deltas, reordered these by just shifting the diagonal entries down once each time in each product. And now I can squish them back together with multiplicativity and gives you lambda 1 up to lambda n in each entry. And guess what I'm going to do next? Pull all of them out. Lambda 1 up to lambda n to the n. And this is delta of 1 now, which is just 1, right? By the multiplicativity. Great, and that proves it, right? So if this is true for all powers of n, then delta of lambda 1 up to lambda n is just lambda 1 up to lambda n.
Don't you run into a little problem when n is even, and you might be only up to sign?
Nope. So there's no change in sign in any of these.
No, I mean, like, because what you're saying is you have one thing to the power n equals another thing to the power n. So if n is even, you can't just like take the nth root and get some
Okay.
fine thing.
Yeah, I see what you're saying. I don't think it matters. I thought about this and I decided that it didn't matter, and I can't remember why. So I guess if you're in the complex domain, we can always pick our roots to be like somewhere here, right? So if this is like 2 pi over n or something, we can always pick our, whatever this delta of lambda 1 is going to lie somewhere in here, delta of this lambda thing. So this is the root, this is the nth root of whatever. So no matter where it lies, we can find one there. I think that's
I
true.
feel like it's only defined up to like action of the nth roots of unity then. Because like, I mean, you're taking something to the power of n. That thing already existed. You can't just decide that when you take the nth root, it's only in
I guess that's true. I'm certain that maybe I made a mistake here.
Could you just use the formula that you had written down and just directly compute what it is?
What formula?
Like the one with each of you to contrast.
So, so what I want to show is that when I start with just these properties, I get something unique.
Oh, okay.
Okay, well, I'm pretty sure, let's talk about it after because you might be right. Instead, let's just take this property, which makes it really obvious. Okay, for now, we'll just take this. And that'll definitely give us this product of lambdas. So we already know now that it agrees, actually, because we know that this thing satisfies these two properties, right? We've taken its existence for granted. We're saying, suppose you're given a delta, satisfies these two properties. We showed the uniqueness of the determinant from before, and we showed it satisfies these two properties. So if it's anything, it's the determinant. There's only one thing that satisfies them. Right? Okay, cool. I think I'm gonna skip. I was gonna talk about the trace for a second, but I'm just gonna skip to infinite dimensions and talk about it when I do it, if I have time. So, okay, so basically, like Basil said, the determinant really is this map, going from lin v to lin v wedge n, right? The question that needs to be answered is, what the heck is this in infinite dimensions? It's not clear, right? So you can, I guess, here, let's talk about infinite permutations. So we can call sim of kappa so if kappa is some cardinal set, we can call sim of kappa the set of bijections from k to k. And it's obviously a group for the same reason as before. We're not going to be able to define a sign for any permutation unit. It's going to be really small, actually, the set of things that we can define a sign for. So, I'll say that. Okay, so where can we define permutations? Well, remember the argument that I was trying to explain before with the big product, right? How well is that generalized to infinite dimensions, right? The only problem is that the product, I'm just going to explain this verbally because I don't know, it might take a little while to write down all the definitions otherwise. The only thing that goes wrong is the product ends up being infinite, right? You can solve that. You can solve the blow up by passing the sign into each argument, right? So instead I'm just taking a sign at each point. Okay, but how do I know I don't have infinitely many ones and minus ones, right? The question, or I guess the answer to that is we're gonna narrow our search to only the things that are generated by swaps. So by swap of kappa, I'll denote the exact same thing that I had before. These are swaps. I pick two elements in the cardinal set kappa and swap them. What can I generate with that? Well, no matter what I generate, it's only going to go up to finitely many terms in the product, finitely many factors, right? So actually, I'll just define this. So let's define the support. This is non-standard. I just didn't know what else to call this. The support of permutation sigma to be all the i's in kappa, I guess, such that sigma of I is not I. So these are all the points that aren't fixed. Right, so in other words, this is the set where anything interesting happens. Off of this set, nothing really happens. So I'm going to again say it's obvious that this swap of k generates the set of permutations in sim of kappa such that the cardinality of the support of sigma is finite, right? So, but again, this is just the same thing I was saying. And now I have an infinitely large deck of cards. If I swap them, if I pick two things, swap them, n many times, I've still only swapped finitely many things. I could only have changed finitely many things. So, so this is going to be finite, and I can obviously reach any of those, anything I try to get through that procedure. Anything that swaps only finitely many things in an infinite list can be generated by swaps. Maybe that was worded poorly, but I think it makes sense. Okay. Yeah. So what was I saying? So yeah, I was talking about the product. So how do we know that there aren't infinitely many minus ones and ones? Essentially, if I want to think about this delta of, say, sigma and gamma, right? These are two permutations. If I want to think about this, I'm just going to truncate the product at the end of each one, right? And it'll work for both of them. Now I can define delta of sigma and delta of gamma. I can pull them apart. It's a homomorphism. We get the exact same argument as before. It's a little hairy as to whether or not it's well-defined. To really make it well-defined, you just want to restrict the product to this set. Right? And so as long as I'm only on this set, which is finite because we're on swaps, it's a finite product. So that's a more rigorous way of seeing that it's well-defined, that it's not going to blow up anywhere. Okay. So using the argument we had before, this is the only, like, off of these swaps, I can't possibly define a sign, right? I mean, you can't find the sign of infinity. It doesn't make sense to ask that question. So, okay. Let me grab the next page of notes. So, I want to talk about so what did we do after we found out that the sign of the permutation was well defined in the finite dimensional case? What we want to do was show that the wedge product is non-trivial, right? We want to show that we can reflect things in however many dimensions and not get back to the original thing if we reflect an odd number of times. It's going to turn out that we have the opposite problem here. So it's definitely not non-trivial, but the size is huge. So I'll say, I'm not going to talk about the wedge product this time as much. I'll just say define it in the obvious way. You swap things based on this group, and pull the sign out depending on the sign, which is defined by the number of swaps. Okay, so and I'll write you could say wedge to the kappa of v, or v wedge to the kappa. Okay, so the question is, what's the dimension? And the answer is really huge. So dimension of v wedge kappa is 2 to the kappa. So how do we know? I can try and not spend too long on the cardinal arithmetic here, but I think it's kind of fun. So first off, let's find what is the dimension of V tensored to the kappa. So we're going to find this and then do the quotient and see if it changes, right? Or see, it's not going to change, spoiler alert, but we're gonna show that. So so how do we do this? So we're going to set epsilon as E1 or EI, or I'll say EK, K and kappa as a basis for V. So how do we do this? So you can show that what I want to show is that this is greater than or equal to 2 to the kappa. Which I think I guess is obvious, right? So this set V to the K contains this basis set for which, V tensor K. So if I pick an element, right, something that looks like this, V1 tensored infinitely many times, right, which is this sort of tensor product, K and kappa, right, of VK, which has an order sort of built in. So we have to well order K, and I'm going to take for granted that K has a well ordering, which it does by set theory, but I'm going to use it to order this. Okay, so how many elements are there of this form? Well, each of these elements, this is the basis for V. So if I replace these with E's, E1, EK, this set, if I take EI1, yeah, I should put I up top, right? Yeah. So IK is an element of kappa as well, indexed by kappa. Each of these elements is a linearly independent vector in here. So this is really where you're going to see that why is this space so huge? Well, we have that every single basis vector basically can be modded out only by finitely many swaps. But there's a huge amount of vectors in the tensor product. So you can really not change anything when you do these reflections in the space. You can reflect, among finitely many of the dimensions, and the vast majority of the space will stay the same. Okay. So how many of these are there? How did I? Sorry. Yeah, I guess this is a k-fold tensor product of or a kappa-fold tensor product of the kappa elements that were originally distinct in V. And so just this set, just this cardinality of V, or of epsilon, is, we pick an element in kappa for each element in kappa. So it's kappa to the kappa, this is 2 to the kappa. This shows that V, which is less than or equal to epsilon, is less than or equal to 2 to the kappa.
Cardinality of epsilon is just kappa.
Cardinality of what?
Epsilon is just kappa. You're looking at EK where K is in kappa, right?
Yeah, what did I do? Epsilon, yeah.
So like you want like the set of all of these bases.
Like I'll call it beta. Beta is this set.
Yeah, it looks like you can find any subset of kappa
Exactly.
is represented by some of one of these weird tensors.
Yeah, any subset and any order.
Yeah. So it's
Yeah, okay. Yes. Okay, so now, so now what I want to do is, we know now that the dimension of, or sorry, I should have said this is the dimension of V. The dimension of V, gosh. Dimension of V wedged kappa min times is this. Okay. So now we know that the dimension of, this is not even a wedge, this is a tensor. Okay, now we know the dimension of V wedged kappa many times. Because we're performing the quotient, this is going to be this. Right? So we know we found this lower bound.
Shouldn't it be less than or equal to?
Yeah, it should.
Less.
Yeah, it should be. Sorry. Wait, what did I do?
Yeah, you kind of like waved your way through it, like you are throwing out a lot, but you know, you're not throwing out as much as like 2 to the kappa things. I think like there is some set theory argument that you have to do there.
Yeah. Hold on. Let me.
And with V wedged to the K, now the order doesn't matter, so it's really subsets of kappa. You're taking finite
But
subsets, right?
yeah, but that's the thing, right? Is we are only modding out by the things that we can define a sign on. So we're not defining out by sim or defining. We're not modding out by sim of K of kappa. We're modding out by the generated.
Yeah, which are finite, just finite
Finite
sets,
swaps.
right?
So you can't like reorder the whole thing. You can only reorder like an initial segment with finitely many swaps.
With finitely many swaps, right? So then, isn't that the same as just like picking finite, is the cardinality of finite subsets of, cardinality of all, yeah, finite subsets of kappa?
No. I think it will. No, it's not, because the cardinality of finite subsets of kappa is just kappa.
Is it?
Yeah.
No.
Okay. I realize the mistake I made here. This should just be equal. Right. This is the cardinality of the basis. We've gone through every single basis element. This is just equal. And you're right. Thanks for spotting out. Well, this should be less than or equal, and this should be equal to the kappa. Is that cool? Okay. Okay. So we want to find an upper bound. I think I'm just going to say, so if we take any element in V, I guess I'll say elements of V correspond to, and I'll say subsets of kappa, right? So I take an element of V, I say, okay, it's spanned by which vectors? What's the index on the vector, right? Which vectors, which basis elements? What's the index on each basis element? That corresponds to something in kappa. So by subsets of kappa, I'm saying pick the basis elements that span the element that you pick from V, okay? So now we've narrowed it down to at least a finite dimensional subspace of V.
Those would be finite subsets.
Yeah, exactly.
Finite.
Yeah. It's just there's nothing topological. So if you take that, you take just this these finite subsets. We also need finitely many copies of C, right? So that's, you should think of that like we're taking this element of in the vector space, pick out the basis elements. That corresponds to finding these subsets, and finitely many copies. By that I should say finite I should say finite tuples, because what we need is an ordered list of coefficients to find the vector that we're looking for, right?
So like for each finite subset of kappa, you have the cardinality of that subset many copies of C that give you the possible coefficients for each basis.
Exactly.
Okay.
Yeah, pick something for each one. And I'm just gonna, in the product, I'm just gonna way overcount this by, because I'm looking for an upper bound, I'm allowed to overcount.
We already have the upper down?
Okay, maybe I'm thinking of this wrong. But, okay, just, yes, you're right. But I need to be careful. Okay, yes. I'm allowed to overcount because I'm finding elements of V. I'm going to show that, okay, well, you'll see. So, okay, so, in other words, V, right, the cardinality of V is counted at least by picking kappa many elements, right, and then giving each one aleph naught copies of C. I think that makes sense. That should be what it is. It should be finite subsets of kappa. So, yeah, finite subsets of kappa. So this is cardinality of this, cardinality of C. This is essentially what I'm saying when I'm counting this. Does that make sense?
So for each finite subset, you have aleph naught many copies of C?
Yeah, exactly.
So
I'm giving myself way more copies of C than I need.
Okay.
Okay.
Nice aleph.
Thank you. Okay, as I said before, this finite subsets of kappa is just kappa. Yeah, I'm just going to take that for granted. Talk about why. Okay, obviously we can toss out aleph naught because we're assuming kappa is infinite, and we'll keep the C. So it's kappa times C. Okay, so this is good. Oh, I made a mistake here. Give me 1 second. Oh, okay, I missed a step here. So, okay, I'm just gonna say this verbally. Okay, okay, I forgot to go from the quotient. Oh, wait.
I think like you might
You know-
be able to hand wave. So like 2 to the kappa, that's the size of all subsets of kappa. So I think you just have to see that like every subset of kappa
Yeah.
is going to give you some wedge product.
I just want to show that, okay, I think I need to ignore what I did here for a second. So, if you go, take the cardinality of finite number of swaps. Well, I guess what is the cardinality of swap of K is aleph naught. So when I quotient out by this, I'm quotienting by aleph naught. Right?
I don't think that could be aleph naught because you could swap like for any element of kappa, you can swap with the first thing. So you have like at least kappa many things in your set of swaps.
We've been composing it as many things.
No, like for each one, like you can just swap once, and then you could have another thing where
Yeah,
you swap.
you're right.
Yeah.
Yeah. Oh my God, I'm not understanding the argument that I wrote down.
Cardinality.
It's really weird, yeah.
I think like also for infinite dimensional vector spaces, you have that the dimension is equal to their cardinality.
Yeah, that's
So you might be able to use that.
true as long as the C is, or as long as the field is small enough.
Oh, so our thing might not be uncountable yet.
Yeah,
Oh,
but
sure.
it's the fact that it's C is why. sorry guys, I don't know. Okay, this makes sense. Let's just say, okay, here's the result that I want. Swap of kappa is less than or equal to kappa. So let me try this down. Cardinality of swap of kappa is less than or equal to aleph naught times, or not aleph naught, is less than or equal to cardinality of finite subsets of kappa times c to the aleph naught, which is just 2 to the aleph naught, times kappa. Yeah. No, what did I do here? Oh. This should be, sorry guys, this should be. Okay, so each, right, okay, so each element of swap of k, that's generated, I guess, by swap of k, is associated to picking some finite subset of that set of kappa, and then we want to give it some order, right? And so there are, whatever the cardinality of that subset is, factorial many ways of ordering it. Okay? But the point is each finite subset only has finitely many ways of ordering itself. So that's what this is. Each finite subset of kappa has finitely many ways of ordering it, or less than countably many ways of ordering itself. And this is less than or equal to kappa squared, because kappa is less than or equal to aleph naught, and this is kappa, and that's just kappa. Or kappa is greater than or equal. So this is the set that I'm quotienting by, and it's appreciably smaller than what we started with. So in other words, I'm getting this, right? Which is just 2 to the kappa quotiented by kappa.
Okay. And, I think like that part of the argument is kind of with the unexpected direction. Because like the swap k is like, that's definitely bigger than k.
Yeah, exactly.
So like thinking about it, breaking down like that, assuming that all goes through, which I think it does, yeah, that seems reasonable.
But the point is that even with kappa many of these things, right? So even if to each element of kappa I assigned a kappa, it still gives you kappa, right? So with the quotient is modifying. Because I'm only taking finitely many elements from this 2 to the kappa each time. Okay, I'm gonna move on. I probably made some stupid mistake here. I don't know why. I don't know what I was thinking when I wrote this down the way I did, but do I have like, I probably have like 10 minutes left? Or,
Roughly, yeah.
okay. Okay, so, but it's non-zero, right? The wedge. It's really huge, in fact. It's too big. So what if we just pick something? What if we just, so that's really, I mean, that is the heart of what's so awful about this, right? Like orientations in infinite dimensions. You know, you would hope that I'm going from the vector space, right? Or going from the k-fold product of the vector space to something simpler, to get some information, but I'm going to something that's way bigger than what I even started with, right? So philosophically, this is horrible. Right? I can't hope to glean more from a more complicated set than what I started with, or very much at least. Okay. Okay, I'm just going to define the determinant the same way that I did before. It's this multilinear thing going from V. So again, let's take epsilon and alt sub kappa of V, which is isomorphic to this thing, V wedged to the kappa dual again. And so there's just as many of these, right?
Now your dual is also really, really big.
Yeah.
Yeah.
I was gonna
Exactly.
ask, is there like a subtlety with that? Finite dimensions, it's-
Yeah, to be honest, I'm not going to use the cardinality after that. I just thought it would be good to see that it's larger than what you started with, right? And so yeah, you're right. This is going to be horrible. Yeah. Okay, but we're okay. What can we start with here? So we definitely want epsilon of so. Well, I guess we'll start by picking some basis, or yeah, let's just pick a basis. So EI or EK, K is in kappa, is a basis for V, and so we're going to get this crazy wedge basis again, right? So epsilon, we'll call by depth of A, epsilon of this crazy thing, so wedge over all kappas. Remember, it's important that this kappa is given a well ordering of A times EK. So this is like the element in here. So that you could call this epsilon is just the linear map, right? Or we can take this AEK, K and kappa. Right? This is the epsilon in alt of K. Okay, so it's multilinear. There's no way we can hope to think about this on almost any operator, right? Like if we go back to our property here, this blows up more than you could. Like we've got this like kappa fold product here. If I want to even talk about, so if I set epsilon of the identity or det of det of 1 equal to 1, right? Then right away, if we hope to have this sort of like this property, we're totally screwed because det of 2 is now 2 to the kappa det of 1. So you can't get very far away from 1 at all, right? We need this if we want multiplicativity. Without multiplicativity, we've lost everything because it's not even. I mean, like what we want is a homomorphism really to preserve some properties. Geometrically, it's not preserving any volume, any notion of volume if we don't have this, because we won't have this multiplicative property. So we desperately need this to be 1, and that's all we can really cling to. There's the saving grace, I guess, is if we take A, yeah, so let's take A as an operator on, I'll say, lemma. If A is an operator on lin v, right? Or I'll say lin w, and w as a subset of, or as a subspace of v is finite dimensional. So not only is this a finite rank operator, right, but its sort of like support is also finite dimensional. So yeah, so if we have this, we can sort of get some property like this, but only for varying, like sort of a finitely many being by a away from 1. So the property it will have is that det of like an a direct sum with the rest of the space is just det of a. And the way that you prove this is pretty immediate, actually. I can just write that epsilon of this big wedge, or big tuple of ek, k, and kappa. This is just, we define this to be 1, right, by setting 1 equal to 1. So if this is the basis that we start with, then this has to be equal to 1, which is also equal to, let's think about the same epsilon now defined on w, right? So this epsilon, I should call it something else. I'll call it omega. So if we take omega now in this sort of like alt sub n of w, right? So if w is dimension n, I'm just taking the top form in w. Then omega of n, right, is equal to this. So I'm sort of, again, I'm like abusing the fact that we have this well ordering on this. Just make it match the ordering of this 1 to n. And make sure that these e1 up to en, the first n vectors in this kappa tuple, correspond to the domain of this a. Right? I don't know if that makes any sense. But what it's saying is when I apply this a plus 1 to this, what does it look like? I'm only changing the first kappa entries. Or not kappa, the first n entries. So it's saying epsilon of, so det of a direct sum I, direct sum 1 is epsilon of, and I'm going to have a of e1 up to a of en, and then I'm going to have like the rest of the tuple is e k such that like k is greater than n, right, up to kappa, sort of. See what I'm saying? So this is equal to omega, which is the determinant on w, is just a e1 up to en. And so I can lift the properties. This is just det of a. Oh, oops, det here. All right, this is just det of a. And so you can lift these properties from a up to this product here. The exact same things hold as long as I'm taking only products of this, right? But this serves to prove this at the very least, right?
It seems like your W, like you're only considering W's that are spanned by like some initial segment, finite initial segment of your ordered basis. Because here you like, at least in this case, you fixed like E1 up to En as the spanning set for W.
Exactly.
Basis.
Yeah, it's the basis, yeah. Yeah, I don't know if that makes sense.
Kind of just like reduced it down to the finite dimensional
Exactly, yeah. So that's kind of the theme is all you can really do is do what you did in finite dimensions, but now there's a bunch of other dimensions around
It's
you.
like unfoundedly many stuff.
You just ignore them, yeah. Yeah, okay, but I'll write down some of the properties that you get. You get, I'm not gonna prove them because I don't have time, but you get det of this, b plus one. You're gonna get the same thing. This is det of a plus one. So I'll just do like a star. A plus one, b plus one. These don't have to have the same rank, the a's and b's. They don't have to be the same dimension. Right, because when you have them together, I can pull them apart just by doing matrix algebra on the top left of this matrix, and then pull it apart using what I showed earlier.
You want to have like that a plus 1 times that b plus 1, because you just wrote b plus 1 right after the a plus 1 on your second line.
Yeah, sorry. Okay, you get all the other properties. We're going to get, I should shrink corollary. Corollary, we also get det of, and here's the other thing we had. Lambda a plus 1 is just lambda to the rank of a times det of a plus 1. So this is sort of the property that we had earlier. I'll also say, as a remark, that an operator of the form a plus 1, when a is of the form that I said earlier, this is invertible exactly when it's injective. So if it's not, we're always going to have the surjectivity if we have the injectivity, because
The a is only on a finite.
exactly, the a is only operating on a finite. It's taking only finite dimensionally many things and spitting out the same type of thing. Yeah, so it's the exact same argument that you would do in finite dimensions. And so we get this det of a plus 1 is non-zero if and only if a plus 1 is invertible. Right, so if it's not invertible, then it's not injective. We can find some basis where we're going to have a 0 somewhere, I guess you could say, in the Jordan form. We get that when it is invertible, that det of a is non-zero by the multiplicativity. That's all I'll say about that. And then I'll wrap up by giving, without saying too much, again, I feel like I'm unfortunately had to skip over the more interesting half of the talk because I took too long, but what do I want to finish off by saying? I guess what we can do, so there is hope beyond just finite dimension, really finite dimensional operators in infinite dimensional spaces, and that's compact operators. So we can take limits of these operators. So now I need to add some topology.
Vaughn,
Can
is
you-
there, like, the last thing you want to say just for the recording's sake, and then, because I have to.
Sure. I guess, okay, so yeah, the idea is you add this topology, which gives you this norm of an operator by summing all of its singular values, the absolute values of the singular values of that operator, which we have on finite operators, and we have on compact operators, right? But we have det is defined on these finite operators, and it's continuous. And so by just doing this like sort of continuous extension, we're going to get all of these same properties lifted to compact operators, but not all compact operators, only the compact operators which have this one summable spectrum, I guess. Yeah, as long as the spectrum is one summable or the singular values are one summable, you'll get something like that. And you can also get a trace, which just gives you the sum of all the singular values. And it corresponds to this determinant exactly the same way that the trace would normally correspond to the determinant in finite dimensions.
Correspond to the determinant?
Yeah, so normally the trace is...
Normally like the sum of algebra.
Normally, well, it's actually always the log of the determinant of the exponent of the matrix, so long as sigma of A doesn't hit this set. I think maybe it's something like that.
You
Zero.
did this, didn't you?
We did, yeah. Yeah. So as long as you miss these, so what you can do is you can define this trace. This is how you would do it in finite dimensions, by the way. You can.
Yeah, I'm used to seeing like e to the trace is det of e to the a. So that's like
Exactly, yeah.
similar
You
to-
just sort of move all the things over to one side. And you can get the same thing, swap the exp and the log for a determinant. That means if you find a determinant or a trace, you can find the other, usually.
I have a question. Did this left to